Hello everyone, my name is Tiara Devi and I will present chapter 12, the metal casting, design, materials, and economics. In manufacturing, engineering, and technology, Kalpakjian. An introduction, metal casting process involves many variables such as material properties, mold design, casting methods, molten metal flow, cooling rate, and rapid gas. All of these factors greatly influence the quality of the final casting. To further discuss with design principles for casting, the characteristic of a suitable for casting, as well as the economic aspect involved. Next, design consideration in casting. This section explains two main principles in casting design. 1. Component geometry design. Avoid sharp corners, use fillets, maintaining uniform mold thickness, and prevent hot spots to avoid defects such as skin. 2. Mold feature design. Arrange the parting line, gate runners, riser, and seals so that the molten metal flows smoothly and solidifies properly, minimizing defects. Next, general design consideration for casting. The general guidelines include avoiding sharp corners, reduce stress concentration, maintaining uniform mold thickness, prevent hot spots, adding the draft so the mold can be applied without damaging the surface, setting dimensional tolerance according to the capability of the casting process, providing always for skincare and machining considering finishing operations such as drilling and clamping. Next, figure 12.1 illustrates recommended design modification to prevent defects in casting. The figure shows how simple geometric adjustments such as adding fillets, removing sharp corners, and smoothing transition in mold thickness help improve molten metal flow and reduce issues like skin porosity and stress concentration. This illustration emphasizes the importance of proper geometric design in achieving high-quality cast component. Next, figure 12.2 present example of casting design that highlight the importance of maintaining uniform cross-section to prevent hot spots and skin cavities. The figure demonstrates how variation in weld thickness can lead to uniform cooling, causing low acid overheating and solidification defects. By keeping the section thickness consistent and ensuring smooth transition, designers can improve solidification patterns and enhance the overall quality of the casting. And next, table 12.1 provides graphic allowance for various casting metals, showing how much additional dimension must be added to patterns to compensate from dimensional reduction during solidification and cooling, as material has different thermal contraction characteristics, and the values in this table have designed and shown dimensional accuracy in the final cast product. This table serves as a practical guide for setting the appropriate synthetic allowance based on the type of alloy used. Next, design for expandable mold casting. Expandable mold casting, such as sand or investment casting, requires specific design rules, such as ensuring controlled solidification, designing process that remain molten longer, using blades designed to retain height, and providing machining allowance that in casting. Next, design for permanent mold casting. The casting requires a small drive, 0.25 to 0.5, to prevent galling. The casting are highly pressed, have a smooth surface, and are nearly safe, so they only require light trimming and usually do not need machining allowance. Next, computer modeling of casting process. Modeling in casting is very important because it involves complex interaction between matter and process variables, and advance in computer and software allow simulation of metal flow, heat transfer, and reversible formation during cooling. This model can predict flow velocity, reserve distribution, moisture zones, grain size, isotopes, and potential defects such as grains. Software like MakeMyself, Bokeh, Solidia, and Absolute facilitates planning, improves quality and velocity, and enables quick response to design change. And next, casting alloys. And this section describes the progress and application of metals and alloys, including casting characteristics, machinability, and weldability. The most commonly used casting alloys are gray iron, followed by ductile iron, aluminum, zinc, lead, copper, malleable iron, and magnesium. In the use, casting segments reach about 13 million tons per year. Next, non-ferrous casting alloy. Common non-ferrous alloys: aluminum lightweight, corrosion resistant, used in automotive and arch vehicle. Magnesium very light, corrosion resistant, used in wheels and engine blocks. Copper high conductivity, used for bearings and wear resistant components. Zinc low melting point, strong knock, used in the casting discipline parts. Tin and lead, corrosion resistant for bearing. High temperature alloy for titanium, spurious refractory metal, nozzle, and jet or rocket engine parts. Next, figure 24 illustrates the mechanical properties of several group of cast alloy. The chart shows that this alloy group exceeded a wide range of strengths and ductility, with casting demonstrating the large variation. This figure highlights how casting condition, composite, and heat treatment significantly influence the final mechanical properties of cast metals. The next, table 12.2 summarizes the typical application and casting characteristics of ferrous alloy used in metal casting. The table compares alloy group based on castability, weldability, and machinability, providing a quick reference for selecting suitable material for specific casting requirements. For example, aluminum alloys show excellent castability and good machinability, making them ideal for components such as piston and clad housing. Gray iron affect excellent castability and good machinability, which is why it is widely used for engine blocks and brake components. In contrast, white iron has good castability but very poor machinability and weldability due to its hardness, limiting its use to wear-resistant parts. Overall, the table highlights how different alloys vary in manufacturing characteristics and help with material selection based on performance and processing needs. Next, table 12.3 presents the mechanical properties and typical application of various types of cast irons. The table compares gray, ductile, nodular, malleable, and white cast irons, highlighting their tensile strength, yield strength, ductility, and common use. Gray iron are available in pelagic, pelagic, and martensitic forms, has a low ductility but is widely used for engine blocks and machine tool bases due to its excellent damping capacity. Ductile iron offers significantly higher strength and elevation, making it suitable for pipes, gear, and highly stressed components. Malleable iron provides good ductility and toughness after heat treatment, commonly used in hardware and railroad parts. White cast iron, characterized by its high hardness and wear resistant, is typically used for mills, rolls, and abrasion-resistant surface. Overall, this table helps illustrate how different cast irons to influence mechanical behavior and stable application. Next, table 12.4 lists the typical alloys commonly used in casting process. The table includes aluminum, copper, magnesium, zinc, and ferrous alloys, summarizing the neutral, catalytic, and stable for casting application. Aluminium alloys are high-clay for the excellent castability. Lightweight nature and good mechanical properties, making them ideal for automotive and aerospace components. Copper-based alloy, known for their corrosion resistance and strength, are used for valves, fittings, and pump parts. Magnesium alloy provides very low height and good castability, suitable for automotive and electronic housing. Zinc alloy with excellent fluidity and dimensional accuracy are widely used in die casting for small, intricate parts. Ferrous alloys, including various grades of cast iron and steel, offer high strength and wear resistant for heavy duty application. Overall, the table provides a clear comparison of alloy types to get material selection based on performance requirement and casting characteristics. Next, table 12.5 summarizes the casting characteristics and typical application of various non-ferrous alloy, including aluminum, copper, magnesium, and zinc alloys. The table compares these alloy groups based on the castability, strength, weight, corrosion resistance, and overall stable for different casting process. Aluminum alloys are shown to have good castability, low density, and versatile mechanical properties, making them widely used in automotive engine parts, bushing, and structural components. Copper-based alloy, known for their excellent corrosion resistance and strength, are commonly applied in valves, pumps, and plumbing components. Magnesium alloy, not for their very low weight and good castability, are frequently used in automotive and electronic housing where weight reduction is critical. Zinc alloy offer excellent fluidity and dimensional accuracy, making them suitable for die-cast components such as small precision parts, connectors, and hardware. Overall, the table provides a practical comparison that helps engineers select the most appropriate non-ferrous alloys for specific casting requirements. Next, ferrous casting alloy cast iron widely used, easy to cast, hard, wind resistant, and metal types. 1. Gray iron, low porosity, engine blocks, motor housing purpose. Ductile iron, strong and flexible, bear transfer types. White iron, very hard, rolling mill, roll breakers. Malleable iron, railroad equipment fitting, electric parts. CGE combines gray and ductile purpose engine blocks, cylinder heads. Next, cast steel cast at high temperature. 1650. Homogeneous can be welded with heat treatment used in mining, heavy construction, and railroad equipment. Cast stainless steel, heat and corrosion resistant, used in chemical and food industry, can be welded and heated. Nickel-based alloy for highly corrosive environment and very high temperatures. Next, economy of casting. Casting costs are influenced by material, equipment, labor, and time. Sand casting is inexpensive, while the casting and investment casting are more costly due to mold and preparation. Additional processes like melting, pouring, heat treatment, and inspection add to the cost. Automation can reduce labor needs and mass production lower the cost per unit for small quantities, and sand casting is more economical. Next, table 12.6 compares this relative cost associated with different casting process. The table shows how this process varies in terms of tooling cost, production rate, labor rates, and overall economic efficiency. Processes such as sand casting typically have low tooling cost but higher labor input and slower production speed, making them suitable for low to medium products. Volume, in contrast, die casting involves high initial tooling costs but offer very fast production rates and no labor required per unit, making it highly economical for large-scale manufacturing. Investment casting and steel mold casting fall between these excellent for fitting good dimensional accurate but at high processing code, overall table, sheet, illustration how class consideration play a major role in selecting the most appropriate casting process for producing quality and part completion. And next reference Kalpakjian S 2010 Manufacturing Engineering and Technology 6th edition First Education. And thank you for watching and next see video.